So let's talk about the appendix for a few minutes. And so we've already covered a little bit of this, but we're going to recover a little bit, and then we're going to go a little bit further. And what we're really going to talk about now are quasi-linear utility functions. So quasi-linear, so partly linear utility functions. So again, this is when our utility function, for amount of good 1, amount of good 2, is plus x2. So it might look something like this. Well, this is some nonlinear function. And so what our maximization problem is max, let's just write it in. If we want to solve for this, we're going to max Vx1 plus x2 subject to our budget constraint, P1 x1 plus P2 x2 equals m. Well, one method for solving this is to take our constraint and kind of put it into our objective function. Here we're maximizing with respect to x1 and x2, but if we do that, we can do like an unconstrained maximization problem as we kind of learned before. So we can turn this into a problem where we're just maxing x1. And we're just rearranging this budget constraint since x2 equals something and plugging that into our objective function. So plus m over p2 minus p1 x1 over p2. All right, we can take our first order condition of this, right? And at the maximum, it has to be equal to 0. So we're taking the derivative with respect to x1. So v prime x1 is the derivative of this first function, this nonlinear function, with respect to x1. And we're going to take the derivative with respect to the second one of x1. Well, here we just get, minus p1 over p2 equals 0. We can rearrange that, and so we have v prime x1 equals p1 over p2. So again, we kind of learned this before, I think, the demand for good 1 is independent of income. Okay, so let's erase this and talk about the inverse demand function here, and then just explore these quasi-linear utility functions just a bit more. So we just found that v prime of x1 equals p1 over p2, and kind of argued that the demand for good 1 is going to be independent of income. Okay, so now, we can rearrange this to get the inverse demand function. And again, now it's just price as a function of x1. So we're just rearranging this and saying p1 equals v prime of x1 times p2, just rearranging this. So this is the inverse demand function here. Once we find demand for good 1, once we find x1, in other words, we can plug into budget constraints, to our budget constraint, to find x2. The amount of good 2. Okay, so let's look at a simple example, so we can think about this relationship. So for example, let's imagine our utility function equals the natural log of x1 plus x2. So this is that nonlinear function. That's that v of x1 is now just the ln of x1. All right, so that means you want to max ln x1 plus x2 subject to p1 x1 plus p2 x2 equals m. Rephrase this as an unconstrained max problem by rearranging and putting it back in. Ln x1 plus m over p2 minus p1 x1 over p2. We take our first order condition. So now our first order condition, again, is a derivative of this function, and that equals the price ratio, right? And so here, 1 over x1 equals p1 over p2. Because the derivative of ln of x is just 1 over x, and that equals the price ratio. So that means x1 equals p2 over p1. Or our inverse demand function, p1, which is, let's say it's a function of x1, equals p2 over x1. This is that inverse demand function. Not sure if I'm going to run out of room here, but now that we know how much x1 we have, we can take that and plug it into our budget constraint to solve for x2. So solve for x2. Hopefully this is somewhat straight. It's almost like these are separate. This is just a separate idea. I'm just saying what the inverse demand function is, but we basically rephrase this as an unconstrained maximization problem by putting the budget constraint for x2, just like we saw in the general example, or the general kind of representation. We take the derivative of this with respect to x1. Derivative of the ln of x1 is 1 over x1. Derivative of the rest of it with respect to x1 is just p1 over p2, so just that part. We can solve this first order condition for x1. So this is the optimal quantity of x1. If we want the optimal quantity of x2, we take this and plug it into our budget constraint. Separately, I'm just saying this is the inverse demand function for this as well, right? This is the demand function, this is the inverse demand function. Okay, solving for, we have p1 x1 plus p2 x2 equals m. x1 equals p2 over x1 plus p2 x2 equals m. Notice that these p1s will cancel out. And if we did this algebra, we're going to get x2 equals m over p2 minus 1. Okay, so those are two, those are like the optimal quantity here. But we need a quick caveat here. So let's quickly erase the board and kind of talk about it. This is only going to, the demand for good one is independent of income, but it can't be completely independent of income, right? If we had no income, we wouldn't be able to afford any of good one. So we need to put a quick caveat on like this result here. So as we just saw, and I kind of said before, the demand for good one in that example we just did is independent of income. And this is generally true for quasi-linear utility functions. But this can, it's generally true, but it can only be true with certain levels of income. For certain levels of income. Of M, or income, right? If M equals 0, you can't afford any of it. So it has to somewhat rely on income is all I'm saying. So really the derived quasi-linear demand is only going to be true with certain levels of income. quasi-linear demand function is only relevant for certain levels of income. When positive amounts of each good are consumed or bought. So in our example that we just did with that lawn function, remember x2 equals m over p2 minus 1. So if m is less than p2, the optimal amount of good 2 is equal to 0. Right? So maybe a better way of thinking about our quasi-linear demand function is that x2 equals 0 if m is less than or equal to p2, and it's equal to m over p2 minus 1 if m is greater than p2. So we just need to add that caveat there, that it's only going to, this demand function that we find for quasi-linear utility functions is only going to hold when our income is above a certain level. Otherwise, you're going to have none of this other good 2. So it's something to keep in mind when using quasi-linear utility.